All right, so now we'll look at some special processes. So these processes are represented on a PV diagram, and these processes are for an ideal gas. Okay, so again, let me remind you of the ideal gas law. PV equal to nRT. Okay, so there is the ideal gas law, and we are going to represent various processes on a PV diagram. Okay, so an isothermal process is one where temperature is constant, and so this would be constant, and again we're always keeping n constant, so this is constant, and so PV equal to constant, that's a hyperbola. Okay. So this is how isotherms look like, and this is a lower temperature, this is a higher temperature. Okay, so as these hyperbola go further and further away from this center, those are higher and higher temperatures, and so on. Okay, so we will consider these various processes. Isovolumetric process is a process where the volume remains constant. So process A is an isovolumetric process. Isobaric processes where the pressure is constant. This is an isobaric process. See, the pressure is constant in that process. Isothermal process is that where temperature is constant. All these guys are isothermal processes. So all vertical lines are isovolumetric processes. All isobaric processes are horizontal lines on a PV on this diagram. Isothermal processes are hyperbolas, okay, the blue lines. And an adiabatic process is no heat is exchanged with the surrounding. This is an adiabatic process. Okay, so if you do an adiabatic expansion, the gas will cool. Okay. And if you do an adiabatic compression, the gas will expand. Okay. So let me show you some of these processes here. All right, so here's an isobaric process, an adiabatic process, isothermal process, isovolumetric process. Okay. And each case we're going from this, so here is our ideal gas in a cylinder, and we'll do various things. So in each case, we're going from the initial to the final state, initial to final state, initial to final state. So we're always compressing the gas, initial, and in this case, the volume is not changing. And you'll notice that in our convention, the work done would be negative if you go from here to there. The work done would be the negative of this area. In this simulation, work done is positive. So their convention is opposite of our convention. Okay, so let's look at an isobaric process. So you're compressing the gas while keeping the pressure constant. So you have to, so let me do this again. So you see, you have to cool the gas, and the temperature of the gas is decreasing. And each of those terms are changing. So the work done by the external source is 18,200 joules. So for our convention, the work done by the gas would be minus 18,200 joules. Okay. And adiabatic processes where you're not exchanging any heat and okay, with the surrounding, and so that as you compress the gas, since no heat was flowing out, the temperature increased. So you'll see that the temperature increases. Okay. The temperature and pressure increased. Okay. And so let me already give you a result that you will see at the end of this chapter. So for an adiabatic process, what we'll see is PV to the power gamma, we'll talk about gamma in later, will be constant. Okay, so here's an adiabatic process, PV And then adiabatic process is like this. So if you're expanding, if you're compressing, you're going in this direction. Okay. And what we are saying is at every point, PV to the power of gamma is constant. So all along that curve, it's along this curve, it's all constant. Okay. And gamma is the ratio of specific heats, molar specific heats. Okay. So we'll come to that. Okay. So, and you can also show that TV to the power of gamma minus 1 is constant. Okay, so these two relationships are related. So for an adiabatic process, PV to the power of gamma is constant and TV to the power of gamma minus 1 is constant as well. All right. So that was the adiabatic process. Okay. Now, an isothermal process is, you'll see that the temperature will remain constant for an isothermal process. And this is the hyperbola that we talked about. Okay. So the temperature is remaining constant. Okay. And here's an isovolumetric process. We are just adding heat to the system. The temperature is increasing and the pressure was increasing. Okay. So you're just heating up the gas. The pressure was increasing, the volume is not changing, and the temperature is increasing. Okay. So there are the four processes, and now you see the value of these diagrams. Okay, so you saw that trying to show that in a real system is complicated, and you don't get a good sense for, well, it's complicated and it's not great for analysis. So these diagrams are great for analysis. So the processes can be represented by various curves on this PV diagram. Okay. All right, again, isovolumetric process, volume is constant. Isobaric process, pressure is constant. Isothermal process, temperature is constant. And an adiabatic process, no heat is exchanged. Okay. Here's a cyclic process. A cyclic process is you go in a cycle and come back to your initial point. And you, of course, saw that that was important because most engines go through cyclic processes. And so that's important. Okay. The work done during a cyclic process, if you're going clockwise, turns out to be the area inside this curve. If you're going counterclockwise, then the work done is negative. Okay, so again, clockwise, the work done is positive and it's equal to the area inside the curve. Okay. Since you go through a cyclic process, change in internal energy is 0. Okay, so again, now we're starting to say things about each term on that first law of thermodynamics. Okay, so here's a cyclic process. Okay, and here is the first law of thermodynamics. And in a cyclic process, this is 0. So the work done during that process equal to the heat added to the system. Okay, so that's what we have to say about those terms in the cyclic process. And that's what we're saying here. Okay. For an isothermal process, for an ideal gas, all the internal energies and kinetic energy. So for an isothermal process, okay, the internal energy is N, the number of gas molecules you have. So this is for an ideal gas. This is the average kinetic energy per molecule. So that's the number of molecules times the average kinetic energy per molecule. But we saw that from last chapter, the average kinetic energy is given by the temperature. Okay. So if in a process you keep the temperature constant, this is constant, that's constant, the internal energy is not changing. Okay. So for an isothermal process, in that any isothermal process, change in internal energy, change is 0. Okay, so for an isothermal process, change in internal energy is 0. And so since delta E is Q minus W is 0, Q is W. Okay. So just like for a cyclic process, any work done during an isothermal process is equal to the heat added to the system. Okay. For an adiabatic process, Q is 0. And so the work done is equal to negative of change in internal energy. So if the system does positive work, it loses its internal energy, decreases. So negative of negative would be positive. Okay. All right, so what we have done so far is, so here was the first law of thermodynamics, and we've said something about each of those terms for the various processes. Okay. Now, we'll give an expression for the work done during an isothermal process. Here's an isothermal process. Again, this is a hyperbola, okay? And so for an ideal gas, well, what we want to do is calculate this area under this curve, which is the work done by the gas as it expands. And so P as a function of V is given by this expression, nRT divided by V. Okay, so that's just from the ideal gas law. Okay, let me, so PV equal to nRT, so P equal to nRT by V. So that's P as a function of V, nRT by V. And the work done is equal to dV, so that's nRT by V, dV. Okay, and since T is constant, this is an isothermal process. V initial to V final, it's nRT log V, V initial to V final, and RT log V final over V initial. Okay. And that's what we show here. So the work done during an isothermal process is equal to nRT log V final over V initial. Okay. So here, this was a simple calculation to do, so that's why we've done it. We've shown you how to calculate the work done during, we've derived an expression for the work done during an isothermal process. Okay. An isobaric process, that's a constant pressure process, that's an isobaric process. Here's another isobaric process. This is an isovolumetric process, isovolumetric process. During an isobaric process, the work done is pressure times the change in volume. Now, if the final volume is greater than the initial volume, the gas did positive work. If the final volume is less than the initial volume, as in this case, the gas did positive work. In this case, the gas does negative work. Okay. If VF is less than VI, then the work done by the gas is negative. Okay. In an isovolumetric process, where the volume is not changing, this is an isovolumetric process, this is an isovolumetric process. In this process, the pressure of the gas is increasing, so you're adding heat. In this process, the pressure is decreasing, you're removing heat from the gas. And the work done is 0. Okay. The area under these curves are 0. So the work done by the gas is 0. All right, now is a good time to pause. So what we have done so far is, again, so here's the first law of thermodynamics, and so for various processes, we said something about each of those terms. Okay. All right, so now we'll talk about molar specific heats, but Let me stop the recording for a second.